Picture a vessel the length of 4 football fields. It weighs over 200,000 tons fully loaded. It carries enough cargo to supply an entire city for months. It crosses entire oceans without stopping. And somewhere on that ship, in a room not much bigger than a living room, 3 or 4 people are responsible for everything. Not the engines, not the cargo, everything. Navigation, safety, propulsion, communication, cargo management, all of it. 3 people. 4, if you're lucky. That doesn't sound possible. And when you first hear it, your instinct is to assume there must be more crew somewhere, hidden below decks, working in shifts, doing the jobs you can't see. There are crew members, but not many. A modern, ultra-large container vessel, the kind that reshapes global trade routes, operates with a total crew of somewhere between 13 and 25 people on a ship the size of a small town. Today, we're going to look at exactly how that's possible and why the real answer is more interesting than you might think. The confusion starts with scale. When you look at a modern container ship, something like the Evergreen-class vessels or the MSC Irina, you're looking at a structure that is roughly 400 meters long with a beam of around 61 meters. The deck alone covers more than 2 hectares. The engine room is a multi-story industrial facility. The cargo hold contains thousands of individual containers, each requiring documentation, monitoring, and precise weight distribution management. Historically, this kind of scale required enormous crews. In the early 20th century, a large cargo ship might carry 60, 80, sometimes over 100 crew members. Engineers worked in rotating shifts around hot, loud machinery. Navigators manually calculated positions using stars and charts. Radio operators maintained continuous watch. Deck crews maintained the ship, managed cargo, and handled mooring operations at every port. So what changed? The short answer is automation. But that answer is incomplete, and it misses the deeper engineering logic behind why modern ships are designed the way they are. Let's establish the real scale of the problem. The MSC Irina, currently one of the largest container ships ever built, has a capacity of approximately 24,346 TEU. That's 20-foot equivalent units, the standard container measurement. Fully loaded, her gross tonnage exceeds 230,000 gross tons. Her main engine produces around 70,000 kilowatts of power. She burns roughly 250 to 300 metric tons of fuel per day at cruising speed. Her voyage from Shanghai to Rotterdam takes approximately 25 to 30 days. And through all of that, the engine room, the bridge, the cargo systems, the safety equipment, the communications, the navigation, a crew of around 22 people keeps the entire operation running. That works out to roughly 1 person per 1,100 containers, 1 person per 10,000 gross tons. The mathematics of modern shipping is, by any historical standard, extraordinary. To understand how this is possible, we need to look at what crew members actually do on a modern vessel, and more importantly, what they no longer have to do. The most common assumption is that reducing crew size means reducing safety, that a ship with 20 people is inherently more dangerous than one with 80. This seems logical on the surface. Fewer people, fewer hands to respond to emergencies, less redundancy. But this reasoning confuses human labor with system reliability, and it's exactly backwards from how modern ship design actually works. The old crew-intensive model wasn't safer because it had more people. It had more people because the systems were unreliable and required constant human intervention. Engines required continuous manual monitoring and adjustment. Navigation required constant manual calculation. Cargo loading required physical supervision at every stage. Each person existed to compensate for a system limitation. Modern vessels were not simply automated versions of old ships. They were redesigned from the ground up around different assumptions. Assumptions about what systems can do reliably on their own and what genuinely requires human judgment. The result is a ship where fewer people manage more capability, not because corners were cut, but because the role of human involvement was fundamentally redefined. On a modern container vessel, the bridge is the command center. During ocean passage, navigation watch is maintained by officers in rotating 4-hour shift, typically 2 officers on watch at any given time with the captain available on call. The bridge is equipped with an integrated navigation system that combines GPS positioning, accurate to within a few meters, electronic chart displays with real-time updates, AIS, the Automatic Identification System, which tracks every vessel in the region, radar with collision avoidance algorithms, and autopilot systems that maintain course and speed without continuous manual input. In open ocean, the autopilot handles steering. The officer on watch monitors systems, updates logs, communicates with other vessels and port authorities, and responds to anything the automated systems flag. The ship does not require a human hand on the wheel for days at a time. What it requires is a trained officer who understands when to override the system and what to do when something unexpected occurs. The engine room is where the largest reduction in crew size has occurred. A modern ship's engine room is monitored and controlled through an integrated automation system, a network of thousands of sensors tracking temperatures, pressures, flow rates, vibration levels, and fuel consumption across every major component. On many vessels, the engine room operates completely unattended during night hours, a practice certified under what the industry calls UMAS, Unmanned Machinery Space classification. The chief engineer and a small team of engineers and motormen handle maintenance, troubleshooting, and system management during day hours. But the monitoring that once required engineers to walk rounds every hour, manually reading gauges and checking equipment, is now handled continuously by automated systems that alert human crew only when values fall outside acceptable parameters. Modern container ships do not load and unload their own cargo. That operation is managed entirely by port facilities. The ship's deck officers supervise the process, verify weights and distribution against the stability calculation, a critical function since improper loading can cause structural failure, and manage mooring lines during port calls. Between ports, deck crew handle maintenance, painting, inspections, equipment checks. It is skilled work, but it does not require large numbers of people when systems are functioning normally. The real engineering insight behind minimal crew shipping is the concept of centralized monitoring with distributed sensors. Instead of placing people throughout the ship to observe individual systems, engineers placed sensors throughout the ship and brought all the data to one location, the integrated control room, typically adjacent to the bridge. A single officer sitting at a monitoring station on a modern vessel has real-time visibility into propulsion performance, fuel consumption, ballast water levels, fire detection systems, bilge alarms, refrigerated container temperatures, and dozens of other parameters simultaneously. A change that would have required a physical inspection in 1970 now appears as a data point on a screen. The human is no longer the sensing system. The human is the decision-making system, which is a fundamentally more efficient use of trained expertise. Ship stability is another area where automation transformed crew requirements. Modern vessels use computerized stability and loading programs that calculate the ship's center of gravity, metacentric height, and trim in real time as cargo is loaded. Any deviation from safe parameters is flagged immediately. Previously, this required a dedicated officer performing manual calculations for hours before and during every loading operation. Propulsion management has undergone similar transformation. The main engine on a modern container ship, typically a two-stroke slow-speed diesel producing between 50,000 and 80,000 kilowatts, is controlled through an engine control room with automated load management, fuel injection optimization, and exhaust monitoring. The engine adjusts its own operating parameters based on sea conditions and commanded speed. What once required a team of engineers monitoring every cylinder head temperature individually is now managed by an engine management computer, making hundreds of micro-adjustments per minute. A typical day aboard a large container ship at sea has a rhythm that is orderly and structured, less like a military operation and more like a facility management routine. The officers on the bridge rotate through 4-on, 8-off watch schedules. The engineers conduct planned maintenance during day hours and respond to automated alarms as needed. The captain reviews reports, communicates with the shipping company's shore operations team, and makes decisions about routing, speed adjustments for fuel optimization, and scheduling. Shore-based support has become an increasingly significant part of this system. Modern shipping companies maintain fleet operations centers, shoreside facilities staffed with engineers, meteorologists, and route optimization specialists who monitor the performance data transmitted in real time from vessels at sea. A shore engineer at a desk in Hamburg may be reviewing the engine performance graphs from a vessel currently crossing the Pacific. If they identify a developing issue, they contact the ship's engineers before it becomes a critical problem. This model is sometimes called remote fleet management, and it effectively extends the ship's operational team without adding anyone to the crew manifest. The 22 people on the vessel are supported by a broader network of expertise available on demand via satellite communication. It changes the nature of what shipboard crew needs to know and raises the standard for the knowledge and judgment each individual must possess. The minimal crew model works reliably under normal operating conditions. It has well-documented limitations at the edges. The most significant is emergency response capacity. A ship with 22 crew members has a fundamentally different capability to respond to a serious onboard emergency, a major flooding event, a fire in the cargo hold, a structural failure, compared to a vessel with 80. Emergency response requires physical presence, people with hoses, people with repair equipment, people conducting searches. Every contingency plan aboard a modern vessel is built around the constraint of available bodies, and that constraint is real. Fatigue is another acknowledged challenge. Maritime regulations, specifically the IMO's Standards of Training, Certification, and Watchkeeping, the STCW Convention, mandate minimum rest hours for officers. But on a small crew, the margin between scheduled work and emergency response is narrow. When something goes wrong at 0300 during a storm in the North Atlantic, the available response team is limited to whoever can be woken from their rest period. Port operations also expose crew limitations. Mooring a large vessel in a busy port requires coordination between the ship's deck team, harbor pilots, tugboat operators, and port line handlers. When port time is short and turnaround is measured in hours, the small crew is at full stretch. Any additional complication, equipment fault, documentation issue, unexpected cargo problem, compounds quickly with a limited number of people to address it. Finally, there is the mechanical frontier. UMS certification, unmanned engine room operation, functions because modern engines are reliable to a very high degree. But reliability is not the same as immunity to failure. When something does go wrong with a major system in an unmanned engine room, the response is inherently slower than it would be with engineers physically present. Most failures are caught early by sensors. The ones that aren't are the scenarios that keep chief engineers awake at night. The answer is yes. And the more useful question is why it took so long to get here and where it goes next. The shift from 100-person crews to 20-person crews happened over roughly 50 years of incremental automation, sensor technology development, satellite communication, and regulatory adjustment. Each step was resisted by maritime tradition, validated by operational experience, and eventually accepted as standard. What we have now is not a minimal crew. It is a redefined crew, one where each person carries a level of multidisciplinary knowledge and system responsibility that would have been unrecognizable to a sailor from 1960. The deck officer who once steered a wheel now manages an integrated navigation suite. The engine room engineer who once walked endless rounds now interprets performance data and makes predictive maintenance decisions. The bar for individual competence rose as the number of individuals required fell. 3 people on the bridge of a 400-meter ship is not recklessness. It is the result of a century of engineering, discipline applied to the question of what humans actually need to do on a vessel, and what precisely they can trust machines to handle in their place. The ship is not running itself. It is running with the minimum number of the right people, supported by the maximum amount of reliable automation. That distinction matters. That raises a natural follow-up question. If automation has reduced crews this far, what does the next step look like? Fully autonomous vessels, ships with no crew at all, are already being tested. The Yara Birkeland, a Norwegian autonomous electric container ship, has been operating with progressively reduced crew since 2022 and is on a path towards zero crew operation. The technology exists. The regulatory framework does not yet. I've covered the engineering behind autonomous vessels in another video, and if you're curious about where this ends up, that's where to look next.